Okay, hello, welcome back. So for the last bit of this module, let's extend the ideas a little further and look at a, a system of rigid bodies, a bunch of rigid bodies possibly connected to each other. So we want to look at a bunch of things. I don't know how to give the title to this video. It's a system of rigid bodies. We talk about generalized forces. And also we introduce a concept called angular velocity coefficient. So all of them in one video, which are all related and tiny concepts. Okay, so let me start again by a refresher. So if I have a system of particles, that is what we had before earlier in the course, and on each particle there is a force acting. So this is F1 acting on particle 1, F2, and so on. This is really not good. So in this case, if you remember, and this was, I don't know, a inertial frame, I had vector Ri pointing toward any of these particles. In this case, I had something called gamma ij, which we define as either partial Ri over partial Qj, or equivalently partial R dot I over partial Q dot J. And because of this dependence or the sensitivity of velocities, we called it velocity coefficient. We called it velocity coefficient. It was a vector. It was essentially sensitivity of velocity of particle I or R dot I to such a difficult word to write. Generalized rate Q dot J. So some kind of sensitivity. And if we had this, we could write the generalized forces associated with any of these Q's or generalized coordinates. Qj in this case was summation of I from 1 to n across all bodies or all particles within the system of Fi, the net force acting on that particle, dot gamma ij. This is how we define, or one way we could define the generalized forces. Okay, that was for a system of particle where we only had forces and there was no notion of rotation. Now we want to kind of extend this idea general framework to rigid bodies. So imagine I have now a rigid body. There is some force acting on it. Maybe there are some moments too. And it has, I don't know, the center of mass. So first of all, I can define a new thing called beta ij, which is similar to what we had here, sensitivity of actual velocities to the rate of generalized coordinates. I can do this as partial omega I. Oops, this is not good. Partial omega I, partial q dot j. And we call this angular velocity coefficient. And it is the same sensitivity of one of these bodies omega I to q dot j. So it's a very similar concept. So let me do this, and these are the names: angular velocity coefficient and velocity coefficients. And yeah, using this, and do I mention it here? No, let me write it down. I can extend these generalized coordinates qj, generalized coordinates associated with generalized what did I say? Generalized force associated with generalized coordinate j is summation of f dot gamma ij plus m dot beta ij. Both of these are I. Somehow I don't write well today. I don't know what is going on. F I dot gamma ij plus m I dot gamma ij, not gamma, beta ij, and summation is over all bodies within our system of rigid bodies. And something to note here is that to write the generalized forces in this form. Imagine I have one rigid body. This is the center of mass, or whatever reference point. If I have a force that is not acting on the reference point, I can, in an completely equal formulation, bring the force to the point acting on that particular reference point and add the moment of that to as an additional external moment. So I can write any combinations of forces and moment at the end of the day by an addition of one force, one net force acting on a reference point, usually the center of mass, plus all the moments of individual forces plus external couples that add up to create an external moment, and those are my mi and fi for each body. So I can do this and calculate the generalized coordinate. So let me maybe an example, not an example, but a demonstration. So I have one body here, one body there. These are all in 3D. I don't know, another body here. All of these are in 3D moving around with some joints between them. You have forces on each of these bodies, and you have, I don't know, relative rotations of one body with respect to another is defined as your generalized coordinate. You can use this formula to find the generalized force associated with any of those generalized coordinates. So I'm going to let this because it was kind of an ugly example. All right, and the last thing I want to show here is why this is the case and why this formula essentially prove it. Feel free to look at it or skip the video. I recommend continuing watching. So to see this, we go back to the virtual work. So for any single body, for any of the bodies in the system, so for instance, body we have some net force Fi acting on that body and Mi, excluding the internal constraint forces. So the virtual work done on this body by these external forces, Wi, is F dot delta R I, let's call it Fi. Fi dot delta Ri plus Mi dot delta theta I. And this delta theta I is a virtual displacement, let's call it not displacement, let's call it virtual rotation, a displacement in rotational domain. Virtual rotation, and I can use this definition of beta I and write these delta theta I to be a summation of all these beta ij delta q j, where j is from 1 to n and little n is the number of generalized coordinates, number of q's. This is a vector, and this one is what we had before. It's a virtual translational displacement, translation. All of these, remember, that are consistent with the constraints within the system. Translation, and we had this before, delta Ri. I can write it as sum of j from 1 to n, gamma ij, delta qi. So in this case, my generalized or virtual work, I'm sorry, is f dot sum j from 1 to n of gamma ij delta q on j plus mi dot sum of beta ij j from 1 to n delta qj. And let me see if I can bring this. This is Fi. Fi dot this. I'm gonna bring these Fi's inside the summations. Let me write it down. Sum of Fi dot gamma ij. This summation is over j This is n. Plus, well, no. This plus m I beta ij delta qj. And now I can add the virtual work done on all bodies within the system. So delta w equal sum of delta w I from 1 to n, which is sum of I from 1 to big N, sum of j from 1 to small n, f I dot gamma ij plus mi dot beta ij delta qj. And this is the same form if I just swap, if you swap the two summations, it becomes in the form of summation j from 1 to little n qj delta qj. And from here you see that this q is essentially the summation from here. So qj equal sum I from 1 to n, big N, of fi dot gamma ij plus mi dot gamma beta ij. And it's what we had up there. Oh, what did I do? All right, so this is how you can handle a body, a system of rigid bodies. You can hopefully easily define some generalized coordinates between rigid bodies that can describe the motion, and write the kinetic and potential energies in terms of those, find the Lagrangian, do the Lagrange equation. The right hand side are the generalized forces, and that is how you calculate them. Although the method is simple, in practice, actually, Lagrangian for 3D rotation of a system of body may become quite ugly and cumbersome. There are some tricks and workarounds to make things simpler. For instance, instead of using Euler angles as your generalized coordinates, you can use something else called quasi-velocities as generalized coordinates and try to write equations based on those. But anyways, this is, at least in principle, the way how you solve it, how you solve equations of motion using Lagrange. That's all I have for this part. I can't remember anything else to add. And yeah, let's close this section here. See you later.